have today Yoshiko Ogata, who's working on quantum spin chains and related topics in theoretical and mathematical physics. She was a graduate at Tokyo University, recently in 21 a plenary speaker at ICMP, and a recent recipient of the Poincaré Prize. We're very pleased to have you, and thank you for being so accommodating with your time. I guess it's already late where you are, and we're happy to hear about invariants, an invariant of symmetry, protected topological phases, etc.
Okay, thank you very much for introduction, Professor Holland, and thank you very much for invitation. And I'm sorry about the change of the schedule. So I'm going to talk about the invariant of symmetry protected topological phases with on-site finite group symmetry for two-dimensional Fermionic systems. And this is based on this paper on arXiv. So let me start from brief explanation about what is symmetry protected topological phases, so-called SPT phases. So very roughly, we consider the following kind of the following set of Hamiltonian. The set of all Hamiltonian satisfying the following three conditions we consider. First condition is that this Hamiltonian should have a unique gap to ground state, namely the ground state should be unique, and there is a gap between the lowest eigenvalue and the rest of the spectrum. And second condition is that this Hamiltonian satisfies some fixed symmetry, let's say G. And third condition is this Hamiltonian can be smoothly deformed into a trivial Hamiltonian without closing the gap. So we are interested in this sort of Hamiltonian. We are interested in the set of all Hamiltonians satisfying these conditions. And we would like to classify them. And classification criterion is the following. We say that two Hamiltonians are G equivalent if they can be smoothly deformed into each other via a path of gapped Hamiltonian without breaking the symmetry. So note that because of this third condition, any Hamiltonian in this set can be connected to each other without closing the gap. But now we have some additional condition here in this classification criterion, that is without breaking the symmetry. So the symmetry should be preserved along the path. Because of this additional condition, this set of Hamiltonian may split into possibly multiple equivalence classes, and this resulting equivalence classes are symmetry protected topological phases, so-called SPT phases. So in this talk, I'd like to consider this problem in two-dimensional fermionic system in operator algebraic setting. That is what I would like to talk about in this talk. And a main result is, in a word, we obtained some invariant of this classification for this system. And the invariant I'm going to describe later, it looks pretty much similar to the one expected from quantum field theory. That is, according to them, a Pontryagin dual of three-dimensional spin bodies. However, it is not exactly the same. In our words, what we got is some doubled version of this Pontryagin dual of this group of spin bodies. And so it looks a bit unfortunate, but we are expecting that part I didn't finish yet, but we are expecting with a CPT symmetry, it should our invariant should be reduced to this one. But this part I cannot guarantee today because it's in progress. Anyway, what I'm going to talk about is this classification program, and I will describe what kind of invariant we got. So that is brief description of the talk, and here is a plan of the talk. First, I would like to explain the setting. So I would like to introduce a new dimensional Fermionic system. And second, before talking about SPT classification problem, I would like to think about a classification of unique capped ground state without symmetry briefly. And then I would like to move to introduce symmetry and consider the classification problem of SPT phases. So that is a plan talk. So let me start from this first part about the setting. So the Fermionic system we are going to think about, it is described in terms of self-dual CAR algebra introduced by Araki. So here I would like to introduce a definition of it. It goes as follows. So let H be a Hilbert space and let C be a complex conjugation. Then self-dual CAR algebra over this pair of Hilbert space and complex conjugation, it is defined as a C-star algebra generated by these things labeled by this element in this Hilbert space, satisfying these three conditions. That is, first, the map from Hilbert space to our C-star algebra, this is linear. And furthermore, there is this anti-commutation relation. And also, adjoint is reduced to complex conjugation in this way. So this is the definition of a self-dual CAR algebra, and a general Fermionic system can be described by this CAR algebra. And our system will be some CAR algebra over some Hilbert space. Now, about CAR algebra, there is a way to construct some family of automorphisms, which goes as follows. So let U be a unitary which commute with this complex conjugation. Then given that there exists an automorphism which I wrote the U here on this CAR algebra, satisfying this condition. In other words, this formula defines an automorphism on self-dual CAR algebra. So there are a lot of such automorphisms, but among such a thing, most important one for us is the case that U being equals to minus identity, which I denoted by theta here. It's important because it gives a grading on our self-dual CAR algebra. Namely, this self-dual CAR algebra can be represented as a direct sum of odd part and even part of this CAR algebra. So like this, our CAR algebra got grading. So it was about automorphism. Now I would like to about the state. So there is a way to construct a class of states, which are called Fock state. It goes as follows. Let P be a projection which satisfies this condition with the complex conjugation here. Such a projection satisfying this condition, it is called basis projection. And out of this basis projection, as I said, we can construct Fock state. Namely, for basis projection, there exists a unique state, which are denoted by omega p on this self-dual CAR algebra, satisfying this condition. So out of a basis projection, we can define some state, which is a Fock state or quasi-free state. So that was a very general description of self-dual shear algebra. And what we are going to think about it is more concrete one. I'm going to think about the following system as, and I will regard it as a two-dimensional fermionic system. Now, so we consider that as a Hilbert space K. Now we take this one, and complex conjugation I take just as a complex conjugation with respect to the standard basis. It may not need to be so, but I take it so. And now, as I said, from the generalized theory, this one has a grading, and there is even part and odd part. I will denote them by this and that. And for also the in our Hilbert space, there is a local structure, and corresponding to that, this sister algebra also has some local structure. Namely, for each subset X, we denote by AX the sister algebra of this two-dimensional fermionic system generated by BF, whose support is under this inside of this X. So this is about fixing the notation. Now, as I said in the beginning, we care about symmetry in this talk. And so I would like to define in this first slide. So let G be a finite group, and let UG be its unitary representation on CD. And we assume that it commute with a complex conjugation. And recall that having such a unitary, we can construct or define automorphism given by this UG, one tensor UG. And this, so like this, we get out of this UG, we get group action on this self-dual shear algebra. So I will consider such symmetry as on-site symmetry. And we will think about this symmetry later in this talk. Okay, so that was the framework which describe a fermionic system. But now I would like to think about physical model on it. And physical model in operator algebraic framework is given by interaction instead of Hamiltonian. So let me explain about it in this slide. So physical models are given by even interaction in this talk. And an even interaction is a map from the set of finite subset of two-dimensional lattice to even part of the fermionic two-dimensional fermionic system, satisfying this condition. Namely, for each finite subset of two-dimensional lattice, we assign some element in this form. And it's supposed to represent an interaction between fermions inside of X. Therefore, it should be self-adjoint and it should be localized in X. So this is an interaction. And now, from out of interaction, we would like to construct dynamics. In order to do that, this interaction needs to satisfy some sort of nice locality condition, and there can be many such a nice condition, but amongst that, the easiest one should be a uniformly bounded finite range interaction, which means the following. Finite range means that there exists natural number m such that pi x equals 0 if the diameter of x is larger than m, literally finite range. And it is uniformly bounded if, again, literally uniformly bounded in this sense. Now, having such interactions, I would like to construct dynamics. In order to do that, we first define the local Hamiltonian. And local Hamiltonian on finite set lambda is defined by this one. Namely, we just sum up all the interaction terms inside of lambda. And then out of this local Hamiltonian, we construct dynamics, Heisenberg dynamics, and take thermodynamic limit. And if our interaction is nice one, like uniformly bounded finite range interaction, then this limit is known to exist and defines a sister dynamics on two-dimensional lattice. Okay, so the point here is that in this operator algebraic framework of statistical mechanics, we do not have Hamiltonian because there is no thermodynamic limit of this guy. However, there is a thermodynamic limit of dynamics. Therefore, in this operator algebraic framework of quantum statistical mechanics, we talk about dynamics instead of Hamiltonian. For that reason, ground state is also defined in terms of of dynamics. And here is this is a definition of ground state. So a tau phi ground state is a state on fermionic, two-dimensional fermionic system, satisfying this strange inequality for all A in the domain of a generator of our dynamics. So this looks a bit strange condition, but actually if you consider this condition, this inequality in usual quantum mechanical setting, you will find that it is actually the same as our usual definition of ground state. And also, as I said in this talk, we are interested in unique capped ground state. So in general, there can be many states satisfying this condition, but the case we are in the situation we consider in this talk is that the case that there is exactly one state satisfying this condition. And we say that dynamics has a unique capped ground state if there is a unique ground state plus gap condition, namely there is a constant gamma satisfying this inequality for all A in the domain of the generator whose expectation value with respect to the ground state is equal to 0. So again, it looks a bit strange condition, but again, if you consider finite dimensional system and consider this condition, then you will be convinced that this just means the difference between the lowest eigenvalue and the rest of the spectrum is at least gamma. And we take it as a definition in our setting, our operator algebraic framework. So that was an explanation about two-dimensional fermionic system. Now, I'd like to move to a classification of a unique capped ground state. So I just introduced unique capped ground state. So what we are interested in is the interactions with unique capped ground state. That is what we are interested in this talk. So and first, I start by the unique capped ground state classification of unique capped ground state phase without symmetry. So let me start. So a classification of interactions with unique capped ground state. Here, what we are interested in, what we would like to classify is this thing, namely uniformly bounded finite range even interaction with unique capped ground state. Now, we would like to classify them, and we would like to classify them and with respect to the following criterion. That is the following: two interactions in this set are equivalent, and I will write like this. If we can connect them smoothly via a path inside of this P in this set. So this is roughly speaking, we would like to know the connected component of this P, but it's too much, quite a rough description. Now, we can consider such a question in quantum spin system. And if we do consider this kind of classification in one-dimensional quantum spin system, it is expected that there is only one equivalence class for this classification. However, in our fermionic setting, even in one-dimensional system, it is known that there is multiple equivalence classes. Namely, this theorem is known. This theorem by Born-Schutz-Padres and Matsui is known. It says that there exists a Z2 valued invariant for this classification. So even in a one-dimensional system, a fermionic system has some interesting structure. So while I would like to explain about this, how this Z2 valued invariant shows up. And the key ingredient for this theorem is the following, Matsui's theorem. It says that in one-dimensional system, unique capped ground states satisfy the split property. So this is a key theorem, and maybe I would like to explain about specify what I mean by split property, because that is a key point for understanding this theorem. So in order to, I would like to explain about this split property, but in order to do that, I briefly would like to recall you some basic things from operator algebra. So basically, I would like to introduce two equivalence relation between states. In order to do that, first let us recall GNS representation. Recall that for any state on omega on a sister algebra A, we can associate a representation of sister algebra on a Hilbert space. And a representation here, there is a notation. And there is a representation of sister algebra on Hilbert space associated to this omega essentially uniquely. And such a representation is called a GNS representation. And frequently we consider the closure of this range of this representation with respect to the strong operator topology, which is I will denote by this, which is denoted by this. And it's also I will also call it a phonome algebra generated by this. Now, with this preparation, let us recall what we mean by two states being equivalent. We say two states are equivalent if the corresponding GNS representation are unitarily equivalent. That's it. So this has a representation pi omega, and this has representation pi phi. And if they are unitarily equivalent, then these states are equivalent. And in that case, I will write like this in this talk. There is one situation which becomes important for us about this equivalence relation. That is this one. Here, alpha is an automorphism. The situation we care about is that omega composed with alpha being equivalent to omega. And when such a thing happens, it's fairly easy to see that there is a unitary U on the GNS Hilbert space of omega, implementing this alpha. What I mean by implementing alpha is just this one. So adjoint of U implement alpha, literally. So that was things I wanted to recall you about equivalent relation. And there is yet another equivalence relation that is quasi-equivalence. We say that two states are quasi-equivalent if there is a star isomorphism from the phonome algebra generated by by the genus representation of omega and the same thing for phi. If there is a star homomorphism from here to there satisfying this condition, then we say that omega and phi are quasi-equivalent. Sorry. So that is what I wanted to recall you about basic operator algebra. And now I'm ready to introduce a split property. So let HI be an infinite dimensional Hilbert space with a complex conjugation, Ci. Here I and I is either L or R, representing left system and right system. And we say that a homogeneous pure state, omega on this self-dual shear algebra over this direct sum of this system, left and right system, satisfies the split property if omega is quasi-equivalent to the graded tensor product of two states. So graded tensor product is just a graded version of tensor product. It has some concrete formula to define, but let us not go into the detail of it here. So basically, this split property is saying that omega being almost like graded tensor product of left state and right state. That is what a split property is telling. And for this split property in fermionic system, there is some dichotomy, which I wrote here. And so I would like to explain about this dichotomy. And to do that, first let me define some terminology. A von Neumann algebra M is said to be a type 1 factor if it is star isomorphic to B of K, the set of all bounded operators on some Hilbert space K. And with this preparation of terminology, now I can tell you the dichotomy about a pure state with a split property. That is the following. Let omega be a pure state, a homogeneous pure state. Homogeneous means invariant under grading. Let omega be a pure state, a homogeneous pure state with split property, and let H pi omega be GNS triple. Then either this or that happens. This theorem is telling you. First possibility is when you consider the range of the right part of the system, of the whole system, we are just taking the right part here. If we consider the right part of the system in the genus representation and consider the von Neumann algebra generated by it, it is a type 1 factor. And furthermore, this is an even part of this one is a direct sum of two type 1 factors. That is first possibility. Second possibility is the opposite. In this case, this one is a direct sum of two type 1 factors, and this one is a type 1 factor. So there is this dichotomy. And the Z2 invariant we saw in this Born-Schutz-Valdez and Matsui's result is this Z2 this invariant Z2 valued invariant we saw in this theorem is about this dichotomy. So simply they take it as Z2 valued invariant is 0 here and 1 here. And so that is where how this Z2 valued invariant shows up. Unfortunately, I cannot say much about unique capped ground, the classification of unique capped ground state for two-dimensional system. We do not have enough information about the structure of agent or unique capped ground state in higher dimensional system. So let me just move to the third topic, that is SPT classification of SPT phases. Now, as I said, SPT phases, to consider SPT phases, we introduce the symmetry. And as we already decided the on-site symmetry, like this way. Now, for this with this symmetry, we say that an interaction phi is beta invariant if each interaction term is invariant. And one important thing to note is that if phi is beta invariant and it has unique ground state omega phi, then this unique ground state is also a beta invariant. Now, introducing this symmetry, what we are as an object we are interested in is the following, namely beta invariant, uniformly bounded finite range even interaction with the unique capped ground. Now we are interested in only in the beta invariant ones. And about this set, we would like to introduce some classification criterion, which is pretty much similar to the previous one. That is two interactions, phi 1, phi 2 in this set are beta equivalent, and I will write like this. If we can connect them smoothly via a path inside of this set. So this is so now we the difference from before is now we do care about symmetry, and we require the symmetry to be preserved along the path. Now, SPT phases is about this sort of classification. However, actually, when one says SPT phases, it may depend on who he or she is, what he or she means. Namely, there can be two different definitions of SPT phases. First one is the one we already saw. The object we would like to classify is this beta invariant or beta invariant uniformly bounded finite range interaction with unique capped ground state. And we would like to classify them with respect to this criteria. But yet there is yet another one, which I told you about in the introduction. Namely, we consider smaller sets than this one. Smaller sets than this one. More precisely, we fix some difference interaction which is of very simple form with a very simple form ground state, which corresponds to the infinite tensor product in one-dimensional, in quantum spin system. So we fix some simple trivial interaction, and we restrict our attention to interaction in here, but which are equivalent to this difference interaction. In the classification of interaction without symmetry. So namely, we care about the interaction which are beta invariant, uniformly bounded finite range interaction with a unique capped ground state, which can be connected to this difference state without closing the gap. That is what we care about in this set. That is the element in this set. Sorry. And the second definition of SPT phase is the classification of this one. We simply consider smaller set. And we consider the classification of this one with respect to the same classification criteria. As I said in the introduction, because we are now caring about requiring the symmetry to be preserved along the path. So even this one may split into possibly multiple equivalence classes. And in this definition too, that such equivalence class is SPT-phases. So because this is considering smaller set, it's easier than considering the whole system. And as a result, we could do this first classification in one-dimensional system, but for two-dimensional system, we could do only this second definition of classification. That is because of the lack of knowledge about unit capped ground state without symmetry in a two-dimensional system. In one-dimensional system, we had we knew about split property thanks to Matsui. We do not have such a thing in two-dimensional system yet. Now, in any case, we would like to find an invariant of classification of SPT-phases, either definition 1 or definition 2. So for the rest of my talk, I would like to think about how to find it. So from where we should start, how we can try to find such an invariant. There is a hint. In the analysis of gapped ground state phases, there is a general guiding principle to find an invariant. That is the following. If you want to find the invariant of the bulk system, cut the system into two and look at the edge. It's sometimes called bulk edge correspondence. And this gives us some guiding principle. And following this guiding principle, we decide to restrict our group action to the half of the system. Namely, in one-dimensional system, we consider group action on right infinite chain, and in two-dimensional system, we consider the group action on the upper half plane. And then try to investigate the effect of this group action to our unit capped ground state omega phi. That is our first intuitive strategy. Now, let me start from one dimension. In one dimension, as I said, because thanks to the Matsui's result on split property, we could consider definition 1, the wider case. And for this classification in definition 1, there is an invariant taking values in these things. Z2, this Z2 is the one we already saw. That is a Z2 invariant of Born, Schutz-Valdez, and Matsui, which exist even without symmetry. And then there is first group cohomology and second group cohomology. Now, I would like to explain very briefly how these things shows up. We already saw this one, but how the rest of the things shows up. In order to see that, I would like to recall you two facts we already saw. So one is the unique capped ground state satisfies the split property. And second thing is that it is invariant under theta phi, under our on-site symmetry. So recalling these things, let us start investigation. So as we saw, split property has this dichotomy, which corresponds to this index this index being 0 for the first case, 1 for the second case. Now, how about this and that? In order to do that, first we record that our ground state is invariant under our symmetry. Now, recall that having such a, in particular, they are unitary equivalent. Therefore, from this generalized theory we recalled before, this beta G is implemented by a unitary in the GNS representation of this state. So there is some unitary VG. I denote by this is a GNS representation. So there is such a unitary VG on the GNS representation, implementing this beta G. What is nice about it is that this adjoint of VG allows us to extend our original beta G to Fermion algebra. We can extend our action beta G to Fermion algebra generated by the GNS representation just by this formula. So that is a benefit of having invariance of beta G. And having that, let us record our guiding principle. We decided that we try, in order to get an invariant, we try to cut the system into two, or and look at the edge, or we cut, and following that, we decided to consider the restriction of our beta G to the right-hand side of the system. So we restrict this action to right-hand side of the system. And as I said, this one gives some group action on this Fermion algebra. And it applies to the even part as well. Like this, out of this invariance, we obtained some group action on this Fermion algebra and that Fermion algebra. And now let us start to find these things in first case. So first, let us look at this even part. This even part, as it is written here, it is isomorphic to a direct sum of two type 1 factors, let's say M1 and M2. And you can actually see that it should, this adjoint of VG, it should do either of the following. First possibility is this M1, this adjoint of VG maps element in M1 to M1, element in M2 to M2. That is first possibility. And second possibility is it switch the switch them. It send M1 to M2, M2 to M1. There is two possibility about the action of this VG. And this, if this two dichotomy corresponds to gives this first group homology. And so that is how this one occurs. Namely, if it remains the structure, it remains M1 to M1 or and M2 to M2, or it switch. If it switch or not determines this second element in the invariant. And how about the last one? To think about it, we look at this part. This one is type 1 factor. Recall that type 1 factor is just a Fermion algebra isomorphic to B of K. So having adjoint action on this one means that having a group action on P of K. But there was some theorem, Wigner's theorem, which was telling us that group action on B of K is always given by unitary. Namely, if there is a projective if there is a group action of B of K, there is a projective representation which gives this group action. And it is well known that projective representation gives second group cohomology. So looking at this type 1 factor, we automatically obtain second group cohomology. We can do the same thing for the second choice, just these are switched, but we can do the same thing and obtain such these things again. So this was a brief description about one-dimensional Fermionic SPT invariant. Now I'd like to move to two-dimensional Fermionic system. The invariant gets more complicated. First, let me briefly explain what kind of thing. So we found some invariant of a two-dimensional SPT, and it's described by these things. So we are having a direct sum of U1 group and the direct sum of Z2 here. And the first entry is a 3 cochain, and second one is a 2 cochain, and third one is first group cohomology or group homomorphism from G to Z2. And our invariant is given as follows, given by such a set, but not only that, but this element should satisfy some fixed relation. And furthermore, not only that, we consider such a triple satisfying some relation, which I will describe later, and divide it by some class equivalence relation. And that is what our invariant is. So this complicated thing, I don't know, it may depend who you are if you find it complicated, but this complicated thing for me is pretty much similar to the one predicted in quantum field theory about a two-dimensional SPT, but not exactly. So such a structure is written, derived explicitly in this paper. And it looks pretty much similar to what I wrote here, what we will see. But the difference is that they don't have this double part. There is only one of them. And that is there is some difference between ours and theirs, the predicted one. I will come back to this point later. So before talking about that, let me explain about more precisely what is this relation and what is this equivalence relation. So so here, as we noted, there is a direct sum of abelian group, either Z2 or U1 here and there. And as usual, I consider pointwise multiplication for that. And now on these things, A plus A direct sum, I would like to introduce some group action given by first group cohomology or group homomorphism from G to Z2 as follows. So let A be some first group cohomology or just group homomorphism from G to Z2. Then we define a group action of G on A plus A as follows. If AG is equal to 0, then we do not do anything to the vector in A plus A, to the element in A plus A. But if AG is equal to 1, we flip the location. That is like this. Out of a group homomorphism from G to Z2, we can define action, G group action, G action on A plus A. Having this group action, now I can define, I can explain what is the relation I talked about here. The relation is the following. So we are considering this kind of triple, and I'm saying that they have to satisfy some condition. The relation I would like to describe is given by usual differential for the action we saw just now. So let A be we consider this triple, and A is the last one, which is group homomorphism from G to Z2. And out of this A, via this group, we can define this group action on A plus A for A being Z2 or U1. Out of that, we can describe, we can define a differential as usual. Having such a group group action, we can always define differential in this usual manner. And the relation I was talking about is this thing, which can be described in terms of the differential which we determined out of this A. And it means the following, it is the following. First condition, it means that this K should be cocycle, two cocycle. That is simply this being equal to 0 for K kappa. And C, we also differentiate this C. And if this is equal to 0, it just means that C is a cocycle, 3 cocycle. But now there is some additional term, which function, which is given by this second term. So there is some deformation of this cocycle. So this is the relation I was talking about. It's simple, but simple, and in fact, it is found in this Pontiac dual. Now, as I said, we consider set of triple satisfying these conditions, but not only that, and I will divide such a triple by some equivalence relation. And the equivalence relation is this one. So let's say this and that are in element in here, and we say that this and that are equivalent if these two conditions are satisfied. That is, first condition is that first this last group homomorphism, they should be equal. And I will write AG to denote the same group homomorphism. Now, second condition is the following. There is some one cochain and two cochain satisfying these conditions. First one, recall that these second ones were just cocycle, two cocycle. And the second, first equation here is telling us that the group homology corresponding to this and that coincides. And second one, again, it's a bit of a deformation of usual homology stuff. So without this, if we do not have this, and if this is a cocycle, then it just means that this the group homology given by this and that are same. But there is some additional thing, additional function, which is given by this second element. So it looks a bit complicated, but one can show that this actually is a equivalence relation, and you can show that this is equivalence relation, and I would divide it. I would divide this set satisfying this condition by this equivalence relation, and I denote it by this symbol. And my main theorem of the talk is that for this the classification of definition 2, SPT classification of definition 2 in two-dimensional Fermionic system, there is this valued invariant. That is my main theorem. So as I said before, this looks pretty much similar to this Pontryagin dual, but it's different, not exactly the same, in the sense that we have double things here and there. But so it's a bit bizarre, but there is hope here that is QFT and condensed matter physics does not need to be exactly the same. Namely, in quantum field theory, there is a symmetry which can be automatically derived from action. Namely, there is SPT symmetry. And I was informed about this from a string theorist. He suggested me to think about this symmetry, and I'm hoping that right now if we add, so in condensed matter physics, we do not have this SPT symmetry automatically, so we have to add it by hands. And I'm hoping that if we add it by hands to our system, I'm hoping that our invariant should get reduced to this one. And I really wanted to finish calculation by today, but unfortunately I could not. So I cannot guarantee here today, but I'm hoping that this symmetry will rescue me. But yes, so as it's almost time, my time is up. Instead of explaining the how to derive this invariance, I would like to finish the talk here. Thank you very much for your attention.
All right, Yoshiko, thank you very much for this talk. Are there any questions?
I have a question, Stefan.
Yes, please.
Okay. Hi, Yoshiko. This is Karl Henning. Maybe you remember me.
Yeah, of course.
Okay. You emphasize that your invariants take values in a group. My question is there a composition of Hamiltonians such that their invariants obey the group law of this group?
Yes, I cannot guarantee for 2 dimensions, but I'm pretty sure it will. But I mean, with SPT symmetry, I'm sure it will. No, I'm not quite sure, but I guess it is. It will be the same. But what I can say for sure is in 1 dimension, this elements. If we if we consider a graded tensor product of systems, then we naturally get a group law of these things, which is not
and graded tensor
simple.
product. You mean you take the same lattice, but you take the tensor product in the at each side, right?
So we take graded tensor product, but the lattice does not need to be too much. That lattice itself does not matter.
Yeah, I wonder whether you also take the tensor product of the lattices in this step.
For this, I really don't feel it needs to.
So the tensor, I think you have the same lattice side. You don't change the dimension, but you take the tensor product at each side.
No, here what I'm thinking is just a simple tensor product. We do not, these should not interact to each other.
Yeah. Yeah, okay. I think I understand. I understand what you mean. Yes. Yeah, okay. Second question is, you have this relation between these triples in the case of 2 dimensions with the group invariance. This relation that you wrote down, does it define a subgroup?
Sorry, say it again, please.
You had this relation here on this sheet that C and kappa must satisfy. Does this relation define a subgroup of this group?
Well, this, so no, so even so in Pontryagin dual things, there is multiplication defined in this Pontryagin dual, but it is not just a product of this times this and this times. It's not that simple. It's complicated, related, complicated way. So it's not that simple multiplication. So I don't know, but okay. I doubt that it is subgroup of much simpler thing. I'm not sure.
Okay, thank you. Thank you very much.
Yeah, sorry.
Other questions?
Can I ask a question? I'm Haotasaki.
Yeah, of course, please.
Yeah. Yeah, this is beautiful. So many questions, but is there a hope of constructing explicit examples by using tensor network or something? Explicit example of which belongs to each of your classification class. I mean, you show constructive.
I don't know. That could be great, but I guess there should be something, but we should talk to PEPS people. Or,
yes.
Yeah, tensor network people, and I haven't done that yet. And anyway, first thing I would like to try, I should make it clear is a free case, probably. But I suspect if all the equivalence class shows up for free case, I'm not sure.
So but, you had this, yeah. I'm sorry, you had this issue about CPT symmetry. I still haven't understood this quite well, but does this apply to free fermions too? Is it possible to write down a free fermion system without CPT symmetry and see if you have something which they didn't have in Pontryagin dual?
So CPT symmetry I'm telling is something from QFT, which is in continuum limit. And the first thing bothering me is how to formulate in lattice system. And I was suggested not to think about very concrete automorphism instead of some sort of automorphism satisfying this and that conditions. So So I don't know
Mhm.
what to answer your question, sorry.
Yeah, but in any case, it seems like you're getting the correct answer. I mean, they missed something by using QFT, and you are finding better classification. Isn't it true?
I do not have so much ambition, but
I do have.
I don't know.
Mm.
I spent quite a bit of time to reduce this doubled structure, but so far it didn't. And there is pretty much a possibility I'm missing something essential. So yeah, but I find it reasonable that QFT, the prediction of QFT where SPT symmetry is automatically satisfied can be reduced. Can reduce the SPT. It should coincide with a condensed matter result if we do require symmetry to be preserved. We do require CPT symmetry to be preserved. Yeah. And there was a paper by some physicists, I think, that they were talking about free fermion, and they were, I think the content was saying that CPT holds automatic or something in some setting, but I didn't really looked into it, so I'm not sure. But maybe in free fermion system, it automatically holds.
Okay, very interesting. Thank you very much.
More questions? Maybe just a question about this this reference dynamics that you introduced. The reference Hamiltonian, which was I think entered in the two-dimensional situation. Could you? Is that a sort of ultra-local Hamiltonian? I went by a bit too fast. And could you say what is the role of this reference Hamiltonian?
It's the role of reference Hamiltonian is that it is it represents trivial phase, which basically means if we consider quantum spin system, it's like on-site interactions. This is on-site interaction, even in this case, and its unique ground state is infinite tensor product in a quantum spin system case. So it's just it's meaning that there's some it's a phase in this classification which include trivial interaction. And we are trying, so it is in this classification, it is connected to trivial one. So by itself, it's not that interesting. But if we introduce a symmetry, then this phase split into several phases. That is SPT phase in definition too.
Okay. Yeah, thank you. More questions? So in quantum field theory, sort of the case of the group action there's a sort of more general notion of a symmetry, which is not connected to necessarily a group, sort of where this group structure is replaced by a modular tensor category. Is there a way of, is there a path to generalize these results possibly to such a much more general setting, or is this does this not seem possible?
to be honest, I haven't thought at all about it, so I cannot say anything. Yeah. So yeah.
That's fair enough. Right. I didn't have the impression that there were more questions. So Yoshiko, thank you very much again for being with us at such a late time in your where you are. And thanks again. I think we'll have our next seminar on, oh dear,
February 10.
On 10th of February. Yes. Thank you very much. And I think it will be Simone Warzel, I think, right, Jochen?
Yes,
Yes.
Correct.
All right. See you. Bye-bye, everybody.
Thank you. Goodbye.
Goodbye or good night.